This morning we have Allender and Hugo Rivera. They were kind enough to report so Eric now is starting with Kolmogorov Complexity for meta complexity and theoreticians.
Thanks a lot. I'm very sorry Richie couldn't be here, and you'll be even more sorry because I'm a poor substitute, but I'm stepping in at the last minute, and what I was asked to do is sort of give an introductory boot camp lecture on Kolmogorov complexity. So there's a ton of information. We won't be covering it. I'm going to just give you a few basics that are relevant and that some of you probably think you already know about Kolmogorov complexity, but maybe you haven't looked into this. So without raising your hands, I hope people are familiar with the fact that there are two basic different flavors of Kolmogorov complexity. The so-called plain version, we use C of x usually to denote that. It's the length of the shortest description such that you pick some universal Turing machine and you just stick with that forever. If you feed that description into the universal machine, it gives you x. And since you've already seen other notions of Kolmogorov complexity where you don't actually produce x, but just given description and the number I can say what the ith bit of x is, these are actually equivalent definitions. So Kolmogorov complexity could have been defined either way. And so these are not the two different varieties. This is the same flavor. The other flavor is so-called prefix free. And I didn't write the definition here because it looks exactly the same. The only difference is what qualifies as a description. So in the prefix free version, if the universal machine given some description outputs x, that implies that for every string z, the universal machine on dz doesn't produce any output. So there's not too much difference between these. C of x is, k of x is at most c of x plus an additive logarithmic term. So you might ask, yes.
Just a question about c of x. So the way it's defined, you don't need to say what happens when I is larger than the length of x.
Yeah, you do.
Could you need?
Okay, so here we're not saying, how do you know what the length is? So you have to pick some convention. And so if the length of x is n and I is n plus 1, well, you'll just reject on both of those. Or you can reject on every number greater than n. Pick any convention. They're all going to give you basically the same notion.
This could be a prefix of a string that has smaller Kolmogorov complexity, and then it would affect things. What to do for us.
I'm not sure I understand the question. I mean, this definition makes sense. And I'm just avoiding the issue about how we specify the length of the string. And I'm going to sweep even more important details under the rug. So yeah, we've got these two notions, and you might ask a reasonable question, why do we need two notions? Well, one reason is that certain things are, this is definitely a simpler definition. So great. Also, it's got the nice property is that the complexity of any string x is less than or equal to the length of x plus some constant, where the constant depends on what the universal machine is that you're using. Not so nice. Yeah, I should make this on a different line. You have to give some space here. Things that are not so nice is that k of x is less than or equal to length of x plus, well, you can't get an additive constant there anymore. You know, you can add a logarithmic term and you can improve that a little bit if you want to, but you can't improve it much. Basically, you've got to have at least log length x. So if you're sticking with prefix-free complexity, you don't have this nice property that the complexity of x is just an additive constant greater than the other thing. But what's a nice property of k of x? Well, the complexity of the string k of xy is k of x plus k of y, you know, again, plus a constant. So the amount of information in xy is just what's in x plus what's in y, whereas it's not the case for c. C of xy is not equal to c of x plus c of y plus order 1. And of course, the reason why is that if you've got a couple of descriptions, you need a little bit of extra information to figure out where one description ends and the other begins. Even more importantly, is that the sum over all strings x, 1 over 2 to the k of x, converges, which means that you have a way to define something that's a lot like a probability distribution on sigma star. And if you do this for C, it diverges. And this property is really, really useful. It's useful for, you know, so what can we say? The Kolmogorov complexity of X, scratch that. In this probability distribution, the probability of X is about 1 over 2 to the Kolmogorov complexity of X. And this is one reason why in the computability literature, you'll find a lot more instances of people using this K notion, the prefix-free notion, than the C notion. Question?
Is it like, can you prove that there's no universal machine that has a measure that captures the
Yes.
property of both? Okay.
I'm not going to do it now, but that's a theorem. This fact that Kolmogorov complexity is related to this probability distribution is known as the coding theorem. And a lot of the theorems in Kolmogorov complexity are kind of trivial to prove once you know what it is you're trying to prove. This is one of the examples where you actually have to do some work in order to prove it. And it's a really nice, useful property. And, you know, it's a question, to what extent can this be done with some sort of resource-bounded Kolmogorov complexity? Sometimes you can make that work, other times not so clear.
Sorry, another question. Are you saying that's a theorem? That's not a definition, or what is it? Theorem?
This is a theorem. So in other words, you can think about the following experiment. You've got this universal machine that is just flipping coins. So it's got some random sequence, and each point it wants to get the next bit if it wants another bit, and it just flips a coin. And so some of the time that's going to output something, other times it won't. And when it does output something, you can ask, what's the probability that it outputs something? And you get this. Furthermore, any time that you try to define something that is like a probability distribution on sigma star, so something that converges and more or less satisfies the axioms of probability theory and is computable, it's going to have probability related to this. And so this is like the optimal probability distribution that you can get. And so there are a number of theorems related to that. And they all kind of are lumped together as the coding theorem. Yes.
So when you define the experiment where the universal Turing machine flips coins, do you have a prefix-free description?
Well, it only works in the prefix-free setting. You can do this same thing using the plain complexity notion of description, but then if, you know, in this experiment, if it decides to output something X, well, it's never going to continue in doing anything else. So it's going to give you a prefix-free notion of descriptions. Okay, so those are the main reasons why we've got these two different notions of complexity. And one other thing I want to emphasize here, I mentioned it very briefly, there's this important property called invariance, which is that if I define Kolmogorov complexity on one machine versus using a different machine, they're going to agree up to an additive constant. And this holds also for K complexity. And the proof of this, again, is pretty trivial, just using the notion of universal Turing machines. But I want to emphasize something that is sort of a pet peeve of mine. Sometimes you hear Kolmogorov complexity called program size complexity. And people say, okay, the input to the universal machine is the program that describes X. Not true. Okay. The universal machine what is a universal machine? Well, it takes some description of a machine, which is like the program, and it takes some data and it simulates the machine on that data. Okay. Now, if you just try to define things in terms of a machine and you want the minimum length or size of a machine in some sense, such that M, let's say running on the empty string, gives X, you're not going to have this property. It's not too hard to show that you can define something like this, but the the complexity of X this way, let's call it C tilde of X, will be less than or equal to, some constant times the length of X, but you're not going to be able to get something like length X plus order 1 or length X times order 1, just because of the syntax of programs. You can try to do clever things using the recursion theorem. It's not going to work. So, that's why I use the term description. It's not a program, it's the program and the data. And that together is what the input to the universal machine is. I mentioned the coding theorem. There's one other really important theorem that holds for these notions of Kolmogorov complexity, which is, again, the important basic theorem that's not so trivial to prove, which is called symmetry of information. Which is the theorem that the complexity of the string that gives you these two strings separated by commas. So you know what's X, you know what's Y. The complexity of that is equal to the complexity of X plus the complexity of Y given X plus or minus order, actually order complexity of X, Y. I'm stating it for K, and it also holds for C, of course, because K and C agree up to an additive logarithmic term. And of course, this is symmetric, which is part of where the name comes from. Yes, log. Thank you. Pardon? Couldn't hear you.
It's an easy proof of it.
Well, yes, yes. So in pure information theory, Shannon's information theory, theorems like this hold without the additive logarithmic terms. Well, we can't quite match that. But it's useful in many different settings in the study of Kolmogorov complexity. And again, this is something that just doesn't hold for certain notions of time-bounded Kolmogorov complexity. And in other notions, it's wide open. So Longpré and Watanabe showed that for certain notions of time-bounded Kolmogorov complexity, if it holds, then there are no one-way functions. And you can see what's going on. If you can think about X and f of X, well, given X, it's really easy to get f of X. Given f of X, it seems to be really hard to get X if it's a one-way function. And so this symmetric aspect just wouldn't hold. And that's a theorem also, yeah.
So when you say K, X, comma, Y, do you mean the string encoding the pair?
Yes.
Y, okay. I just meant,
So,
like this.
just think of X comma Y being double all the bits of X, double all the bits of Y, and have a comma symbol that's just 0, 1. Okay. So those are a few of the basic theorems of general Kolmogorov complexity. The other important theorem that I guess everybody here probably knows is that all of these notions that we've put up here are not computable, which of course is why, or one reason why there's so much interest in having computable notions. What you might not know is the degree to which these things are not computable. So let's focus on the random strings. So let's say R sub C is the set of all X such that the complexity of X, in order to be consistent with what I'm going to do later in the talk, let's say things that are pretty random. So have complexity at least half the length of the string. And similarly, let's say R sub K is the same thing defined in terms of K complexity. So what? Here's a theorem. The halting problem is weakly truth table reducible to the random strings, no matter how we want to define that. Now, I'm sure, let me just have a show of hands. Anybody have any idea what I mean by weak truth table reduction? Of course not. Oh, great. Okay. So you all know what a Turing reduction is. You know, you use this as an oracle, you can solve the halting problem. It's going to be a truth table reduction. It's non-adaptive, which means I can actually just ask an exponential number of questions to these oracles and get enough information that I can solve the halting problem. However, what I'm going to do is I'm going to use this oracle. So given M and X, I want to know if M halts on input X. Using this oracle, I can compute a running time that's astronomically huge, uncomputably huge, except with the aid of this undecidable oracle. And then I just run M on input X. If it doesn't halt, I say, yeah, it's never going to halt, because the running time I've computed is big enough that if it hasn't halted by then, it's never going to halt. In other words, this weak truth table reduction is one where the running time is uncomputably large. Okay. A neat and kind of amazing theorem is that for the C notion of complexity, you actually can put a bound. Basically, there is, the halting problem is time t reducible to the C random strings. You might ask, well, what's the running time? In the current proof, it depends on the choice of universal Turing machine that you're using to define Kolmogorov complexity. So for certain, actually, the best that we know is that there exists a universal machine such that the halting problem is in deterministic time, I think 2 to the 2 to the n relative to the Kolmogorov random strings using machine C, using universal machine U. Can you do better? Well, we don't know. For the particular type of reduction that this theorem has done, which is the so-called disjunctive reduction, basically you just write a list of strings and say, hey, are any of these random? There you can prove that there is no single running time that you can use that works for every machine. So, an open question is whether or not the halting problem is in P relative to the random strings. For some machine, for some universal machine, for every universal machine. Either way, we have no idea. So that's, I don't know of any application to rest of complexity theory to be able to answer that, but it's just a weird open question that, yeah.
The oracles relative to which it's true or false, like the open one.
I don't know that that has been looked at. Okay. What has been looked at is what about if you try to do this with prefix-free complexity? And there, there exists a U such that the halting problem is, is in, let's say, doubly exponential time, 2 to the 2 to the n relative to the k random strings. And there exists another machine such that is not, for every time-bound t, for every computable time-bound t, it's not in deterministic time t relative to the Kolmogorov random strings. And so this is an instance. Let me back up. What makes Kolmogorov complexity interesting is in part this invariance theorem that says it doesn't make any difference which universal machine you use, except sometimes it does. And this is an example where, yeah, sometimes it does.
T needs to be computable.
Yeah, you know, when I'm talking about well, the definition of a truth table reduction in the computability setting is basically that there is a Turing reduction in some computable time bound. You know, it's always going to halt for every oracle that you use, which is the same thing as it's going to halt if you have the empty oracle, which means it's a computable time bound. Yeah.
Many one reductions, can you rule out more stuff?
For many one reductions, you know, first of all, what is the set of all languages A such that A is M reducible to the halting problem? And let's say AC0 or even NC0 reducible to the halting problem. This is something you all know, whether you know it or not. It's just the computably enumerable sets. I mean, it's the halting problem is complete. It's complete with reductions, you know, where you've got your hand tied behind your back, whatever. What is the set of things that are polynomial time reducible to, let's say, the C random strings or the K random strings? Karp reductions. What can you reduce to this undecidable set with an M reduction? Nothing outside of P. Okay, M reductions are useless when you're reducing to the Kolmogorov random strings. Pardon?
Computable sets.
Thank you. Intersect the decidable sets is P. You know, with the modulo, the usual things. Well, there's empty set and sigma star you can't do, but okay. So yeah, for decidable sets, which are the ones we care about, M reductions are useless to talk about the C random strings. And this is sort of a, you know, what do we think? Let's look at some decidable notions of Kolmogorov complexity. You know, A such that A is polytime M reducible to, let's say, the random strings using the KT definition of Kolmogorov complexity that was discussed yesterday. You know, a lot of people would conjecture maybe this is all of NP. Okay, so you seem to get more with a weaker oracle than with a more powerful oracle. This is not weird. This is actually what you expect with an M reduction, because M reductions on the no instances have to produce complex strings. Or actually, the way I did it here, on the yes instances, they have to produce complex strings. You just can't do that with a computable reduction. So even, you know, if you want to compare these two sets, the things that are M reducible to the random strings using that notion versus the things that are reducible to the Levin random strings, you actually expect that these are going to be incomparable. But it should not be surprising that there are going to be things reducible to this easier oracle, which is in NP, that are not going to be reducible with this type of reduction to the more powerful oracle, which is complete for exponential time. So And it's, again, just due to the difficulty in formulating meaningful queries. So if you look at more powerful notions of reducibility, then this goes away to some extent. So
Sorry, I missed the last. Like, why is it that a yes instance needs to have small Kolmogorov complexity? Because you're given the
So
instance, right? So
the so let's do this theorem. Let A be decidable and A polytime M reducible to the C random strings. Then A is in P. Proof. Why is this true? Let X be equal to the set of all. Got this reduction. Let F be the function that reduces A to R sub C. Let X be equal to the set F of X such that X is in A. This is a subset of R sub C, right? Because that's what reductions do. This is finite. Because if you've got infinitely many things, you know, it's finite. Let's just write it that way. Less than infinite. If you've got infinitely many strings in there, then you can say, okay, given n, give me the first string in X of length greater than, I don't know, 2 to the 2 to the n. You can find that. And you've got a really short description of it. It can't be random. There's the contradiction. Okay, so for M reductions have a hard time with, that's defined in terms of Kolmogorov complexity. There was a question that Han Lin asked yesterday, which I made a note of, and it was basically Valentin proved the theorem, or mentioned the theorem, NC1 is contained in the class of things that are AC0 reducible to MCSP. And this was a non-uniform reduction. And Han Lin asked the question, well, what about uniform probabilistic reductions? Actually, I don't think we know anything much more about this, but we really know pretty precisely what is the set of all A such that A is, let's say, randomly reducible to, let's say randomly AC0 reducible. I'll write R AC0 M reducible to MKTP. Do I need to remind people what MKTP is? You've been hearing over and over and over again about MCSP. And this is where the complexity measure is circuit size. And if we just replace circuit size with this time-bounded version of Kolmogorov complexity, you get MKTP. And I should explain what actually I'm going to do this, make this correct. I'll make it a BP AC0 reducibility. This is a reduction where we're even going to define this for promise problems. So you've got yes instances and no instances. And here's MKTP. So we've got the yes instances for MKTP and the no instances. And a BPAC0 reduction is something that takes input X and a bunch of random bits and produces outputs Y, such that if X is a yes instance, we're almost certainly going to end up with a yes instance. And if X is a no instance, we're almost certainly going to end up with a no instance. So it's an M reduction, but probabilistic. And you've probably, most of the people here have seen probabilistic reductions one way or another. So this class, the class of things that are reducible to MKTP, contains a complexity class that nobody here almost has ever heard of. This contains the complexity class NISZKL. People here have heard of interactive proofs, right? I don't need to explain interactive proofs. Probably most people here know about zero knowledge. And well, there's computational zero knowledge. There's also statistical zero knowledge. And statistical zero knowledge is what you get where you've got a prover or a verifier interacting with a prover in the usual way of interactive proofs, where for the yes instances of the problem, there's also a simulator that can produce a distribution that looks, doesn't even look, it actually is very close to the distribution on conversations between the actual verifier and the prover. And with the non-interactive version of this, the prover and the verifier can each see the input X, and they each see some random bits. And the communication is just that the prover talks to the verifier. There's no further interaction. And this is something that cryptographers were really interested in, because it gives them, you can have some interesting protocols for interesting problems in that way. And the nice theorem is that statistical zero knowledge and NISZK have essentially the same complexity. If you've got anything you can do with an ordinary statistical zero knowledge protocol, there's something in non-interactive zero knowledge that you can reduce to it. You can reduce it to. So there's something hard here, if and only if there's something hard there. And this is closed under complement. We don't know if this one is, and so here's co-NISZK. And I actually wrote this wrong. This is co-NISZK-L, which is reducible to MKTP using these AC0 reductions. What's the L stand for? Well, for various reasons, different people introduced log space versions of this where the verifier and the simulator are log space computable. A lot of the problems that people are interested in that are in SZK are in SZK with these log space computable verifiers. And it turns out that there is some other stuff you can do in the log space setting. And one of those things is that you can get MKTP hard under these probabilistic AC0 or even NC0 reductions. And one reason that I'm introducing this now, or mentioning this now, is that you get even a nicer connection if you look at the non-computable version of Kolmogorov complexity, namely that A, be a promise problem, and let's let it be decidable. So the yes instances are decidable. The no instances are decidable. Then A is in NISZK if and only if A is BPP honest M reducible. Honest just means you don't ask really short questions. To the Kolmogorov random strings, I'm putting a tilde over there. What's that? X is in the yes instances for RK tilde if the K complexity of X is greater than or equal to the length of X over 2. And it's a no instance if and only if K of X is less than or equal to length of X over 2 minus an error term, where the error term can really be almost anything. Logarithmic, super logarithmic to n to the little o of 1. So what? This is not computable. We've established that. Actually, for 20 years, yeah.
I think that implies it.
Yes, if and only if. So for 20 years, I've been trying to get my hands on what is efficiently reducible to the Kolmogorov random strings or to the problem of computing Kolmogorov complexity. And I made a bunch of really bad conjectures, many of which were disproved by Shuichi Hirahara. But these conjectures were of the form, maybe we get a really nice familiar complexity class by looking at things that are reducible to the Kolmogorov random strings. And it turns out that if you use the right notion of reducibility and we allow a lot of don't care conditions, so we're just asking about approximating the Kolmogorov complexity. And if you're generous in your notion about what's a nice complexity class, well, it works, that it actually happens. And the thing that's sort of shocking about this is that, it shouldn't be, right? I mean, this is something that people who are interested in building smart card machines, you know, ways that you could prove your identity quickly without revealing information. A practical notion, you know, it turns out to be exactly characterized in terms of reductions to this non-computable notion. And this is another example where if you look at the KT random strings or something like MKTP, that should be, it's decidable. It's sitting inside NP. It's not expected to be reducible to this undecidable thing, because that would put this thing that's hard for co-Nizic inside Nizic. And in fact, it even gets weirder than that. Remember, I introduced this log space version. We can also say A is in Nizic L if and only if A is random log space honest M reducible to R tilde K, or A is random NC0 honest M reducible to R tilde K, or anything in between, or BPP versions also, A BP L honest M reducible to R tilde K. Basically, any kind of not very powerful probabilistic reduction gives you this log space class. And I've got 10 minutes left. So let me just mention one other thing that you get out of this. So, but I started to mention, this is another example where the things that you can reduce to a more complex set maybe is a smaller class than the things you can reduce to a less complex set like MKTP. Because if that weren't the case, then MKTP would actually be in here, and then a bunch of really weird stuff happens. So if MKTP is in NISZKL, then let's look at the complete language for Nizic L. Complete language for Nizic L has my initials. Entropy approximation is the set of all circuits C, well, the yes instances, are the set of all circuits C and number K, such that the entropy of the distribution represented by C is greater than, let's say, K plus 1, and the no instances the set of all pairs C, K, such that the entropy of the distribution C is less than K minus 1. So, in other words, your input is a circuit that takes a bunch of random bits as input and produces some string Y as output. So it imposes a distribution on the Y's, and the question is, what can you say about the entropy of that distribution? Yeah.
This is for Nizek, not Nizek L.
Yeah.
Right.
Right. So for Nizek L, this is an NC0 circuit. Or it could be a branching program. Either way, you get something that's complete for Nizek L. Now, unconditionally, we know that this problem, the complement of it, is reducible to MKTP via a probabilistic reduction, but also co-Nizek L is projection M reducible to MKTP. A projection is a reduction. I mean, here's an NC0 circuit, which just means that every output bit depends on a constant number of input bits at most. A projection is where that constant is 1. So every output bit, basically there are no gates. There are just not gates. There are wires that feed inputs to outputs. So in other words, these projection reductions aren't really doing much of computation at all. They're just plugging the input into a template. And you know, SAT is complete under projections. These problems are complete. Just about any complexity class you're interested in, the complete problems that you're familiar with are going to be complete under projections. And so in some sense, it's not too shocking that you can show that this thing is, that we know is complete under some other notion of reduction, is complete under projections. Except that we don't know, and what else do we know? This thing also projection reduces to the Kolmogorov approximation problem for random strings. So these are non-uniform, and in fact, that's crucial. Well, I mean, actually, for this result, it's not inconceivable that they could be uniform somehow. But if MKTP is in this class, which contains a fairly good sized chunk of P, actually, the determinant is in here. If MKTP is in that class, then there exists a projection F such that if KT of X is small, that implies that the Kolmogorov complexity of F of X is big. So, you know, it takes the all zero strings and outputs something with high Kolmogorov complexity. That can only happen with a non-uniform projection, but it could happen. But also, if you take anything that's got high complexity, then it's mapping it to something with significantly lower complexity. Minus, you know, something big, 2 to the, let's say, square root log n, something like that. So in other words, you take something that's got almost no information at all, and you feed it into this little device, and you get out a bunch of information. But if you feed a bunch of information into it, you get out not much. You know, it's like you pour water in and you get milk, and you pour milk in and you get water. And we understand computation so little that if it weren't just a projection doing that, it would be hard to say, well, why not? But projections aren't really doing much. And also the fact that the thing we're reducing it to is basically an information theoretic object. There's things that either have a lot of information or not very much information. And also, with this is the fact that in order to get this type of result, we're using some non-relativizing proof techniques. I mean, it's reasonably plausible that one can just show that this can't happen. And if you can do that, well, then you've separated NP, which contains MKTP, from non-deterministic log space or a bunch of things. So this probably won't work. Almost, nothing else has worked, but it's worth at least trying to figure out if it might work. And so, if people ask what's a goal for the semester, for me, a goal for the semester is separate NP from log space. Show that this will work. And I'd be happy with that. So I didn't cover everything I thought I might cover, but I've used up my time, and I yield the floor. Yes.
So you were saying there exists a projection F, and this is the same projection for both of those?
Yeah, actually, the argument that shows that this works uses the fact that, I can just show you what the projection looks like. Here we've got this NC0 circuit. I want to know what its entropy is, right? So I just take a bunch of copies of it. Take a bunch of copies of it and feed different random strings into it and get a bunch of samples, and I just concatenate them. And in fact, we can say that the KT complexity of this string gives you a pretty good estimate of the entropy of these distributions. And so asking what's the KT complexity of this allows you to say it's got high entropy or low entropy. And one side of that is basically just a counting argument using the fact that most strings have high KT complexity. Well, they've also got high K complexity. So this projection maps low entropy distributions to things with low KT complexity, high entropy distribution things with high K complexity. And it's probabilistic, but you just hardwire in a choice of the random bits. And I forgot to mention that you can build this, EA is complete under projections for these the NC0 circuits. You can build them from input X via a projection because, for the completeness for this problem. And so each output bit here depends on a constant number of random bits and only one bit of input, X. So when you hardwire in the random choices, a lot of this simplifies to just constants, but everything else just depends on a single bit, and that's your non-uniform projection. So yeah, it's a pretty simple construction. Yes, there's a question here.
I'm not sure I understood everything, so this might be a really bad question, but if it weren't non-uniform,
then it would be sort of easy to disprove.
That's right, because if you've got a computable function, you feed low complexity in, you get low complexity out.
So the problem is the fact that we've hard-coded those bits. That's the issue. So
On the other hand, we know a lot, it's a uniform way that we build this. And so, we start off with a fair amount of information and I don't know.
If I change the K in the consequences of these, so like, I don't know, KT, then like, if you assume NP equals log space, can you make the projection uniform?
I don't know how to do that. No.
Because then you can at least verify, right, the projection is not, so it seems like you could make it uniform in that case, but it would be a different kind of statement.
Yes. And Eric Wong. We convene in half an